In this video, we are going to talk about radical substitution reactions. We have seen that the carbon-carbon double and triple bonds of alkenes and alkynes are composed of strong sigma bonds and weaker pi bonds. And because of their relatively weak pi bonds, both alkenes and alkynes can undergo electrophilic addition reactions. And because alkanes do not have any pi bonds, they cannot undergo electrophilic addition reactions. And normally alkanes are very unreactive compounds because of two main reasons. The first one is they have only strong sigma bonds. You can see that there is a sigma bond between carbon and carbon, and there is a sigma bond between carbon and hydrogens, right? And because of this reason, they cannot undergo electrophilic addition reaction. And the second reason is that they don't have any partial charges. Say, for example, the electronegativity of carbon is 2.5, whereas for hydrogen, it is 2.1. There is no significant electronegativity difference between these two atoms, and because of which they cannot act as either nucleophiles or electrophiles. And because of these two main reasons, alkanes are very unreactive compounds. But alkanes can be forced to undergo some reactions, and one of these reactions is halogenation reactions. Okay, and for halogenation reactions, we need to have high temperatures or light. Let us look into two halogenation reactions here, chlorination and bromination. Methane, when it is reacted with chlorine in the presence of heat or light, it is being converted into methyl chloride. Okay, here we have ethane. Ethane, when it is reacted with bromine, again in the presence of heat or light, it's going to get converted into ethyl bromide. Okay, so when you do a halogenation of an alkane, it is going to get converted into the corresponding alkyl halides. Now, if you want to understand the mechanism for the halogenation of alkanes, then we have to first understand what is heterolytic and homolytic bond cleavage. Let's consider the bond between atoms A and B. And let's also draw the electrons that are present in the bond. We know that each bond is made of 2 electrons. So let's draw those 2 electrons here. If both of those 2 electrons is going to go to one particular atom, it is going to be called as heterolytic bond cleavage. So here in this case, both the electrons are going to go onto this atom, and therefore the atom A is going to have a positive charge on it, and the atom B is going to have a negative charge on it since both the electrons have gone on to B. The term hetero means different and lysis means cleavage. The homolytic bond cleavage happens in such a way that the bond cleaves so that one electron goes onto each atom. So here are 2 electrons that is making up the bond, but when this bond cleaves, one electron is going to go onto each atom, and they have to be represented using the fishhook arrow. So an arrowhead which has only one barb. So this is definitely different from what we have written down here, right? So this is a complete arrow, whereas this one is called as the fishhook arrow. Okay, representing that one electron is going to go onto one atom. And the product of the homolytic cleavage is going to be free radicals. So it's going to form 2 free radicals here in this case. Okay, and the free radicals are generally highly reactive because when they acquire an electron, it will result in the completion of the octet. Okay, now let's look into the chlorination of methane. Methane undergoes halogenation with chlorine, okay, to give chloromethane. Okay, in order for this reaction to happen, we need to have light or heat. Light is represented by the symbol H nu, and heat is represented by the symbol delta. Any radical reaction is going to take place in 3 steps. The first step is initiation, second step is propagation, and the third step is termination. In the initiation step, a new radical is created. new radical is created. In the propagation step, one radical is converted into another. So basically this is radical conversion. And then in the third step, which is the termination, two radicals combine together to form a molecule. Now let's apply all of these in our halogenation of methane. Okay, in the first step, what's going to happen is the heat or the light that's supplied to this reaction is going to break the chlorine-chlorine bond homolytically. So we know that each of this chlorine is going to have 3 lone pairs of electrons, and then this bond right here is made of 2 electrons, and one of these electrons is going to go on to one atom and the other electron is going to go on to the other atom, causing a homolytic fission. Okay, so that's going to result in 2 chlorine radicals, which is going to look like this, right? And in the next step, this chlorine radical that has been formed is going to actually remove a hydrogen from our methane molecule. Okay, so this is a chlorine radical. This chlorine radical is now going to react with our methane. Okay, so this is methane, where we're going to pull the hydrogen from this methane to form a methyl radical. So again, this is also going to be homolytic cleavage, where the bond right here is going to break and it's going to try to form a bond between hydrogen and chlorine, and a methyl radical is created, right? So let's draw this one. So it's going to be a methyl radical and HCl. So remember, a propagation step is a step where one radical is converted into another. Here, a chlorine radical is converted into a methyl radical. So definitely this is propagation, because this methyl radical propagates the chain. Now in the next step, this methyl radical that's been created is going to react with another chlorine molecule to break it homolytically. Okay, so the electrons in here is going to come here to try to form a bond between carbon and chlorine, and a new chlorine radical has been created. Okay, so that's going to result in the formation of our compound and also another chlorine radical. So again, this is also another propagation step where one radical is converted into another radical. Okay, and the last step is going to be termination step, where 2 radicals combine together to form the neutral molecule. So what are the radicals that are being created here? So we have methyl radical, we have chlorine radical. So either 2 methyl radicals can combine together to form ethane, or 2 chlorine radicals can combine together to form chlorine molecule, or a methyl radical can combine with a chlorine radical to form methyl chloride, which is a product, right? So in the next step, what's going to happen is the 2 chlorine radicals will combine together to form the chlorine molecule, and a methyl radical and a methyl radical will combine together to form ethane, or a methyl radical can combine together with a chlorine radical to form chloromethane, which is the product. So radical reaction needs to come to a completion, and that completion happens through these steps, through these termination steps, where the 2 radicals combine together to form the molecules, neutral molecules. Okay, and the mechanism for bromination is going to follow exactly the same pattern. All you have to do is just substitute this with bromine, and the bromine radicals are going to be created, and the steps are essentially the same. So this altogether is called as the radical substitution reaction, where you can see that the hydrogen here in the alkane has been substituted for the halogen. Okay, and it has to follow all these 3 steps: initiation, propagation, and termination. Okay, when you do an halogenation reaction of an alkane, you need to always make sure that there is excess of alkane. If you do not have excess of alkane, then it can lead to dichlorinated product, trichlorinated product, and even tetrachlorinated product. So let's see a scenario here. Let's consider the reaction where methane reacts with chlorine to form chloromethane. Okay, so here in this case, we know that the chlorine radical is being obtained in the first step, and this chlorine radical can actually react with a chloromethane, where one of the hydrogens in here is being replaced by the chlorine to give dichloromethane. And again, this dichloromethane can react with another chlorine radical to form trichloromethane, which is chloroform. And then this trichloromethane or chloroform can react with another chlorine radical to form a tetrachloromethane, okay, carbon tetrachloride. Okay, so in order to avoid all of these steps, you always need to make sure that you use excess of alkane. This is going to potentially avoid the collision between the chlorine radical with the substituted products.